Now, today's lecture is much shorter than previous one. I'll start solving problem number 1 on gravity. If we have a satellite rotating around the Earth, this satellite has a mass equal to 3,000 kilograms. The mass of the Earth, as you know, it is 6 multiplied by 10 to 24 kilograms. Okay, what else? The period for the rotation, tau. Or omega now. Omega is 2 times rotating about Earth, around Earth, twice a day. So omega is 2 times 2 pi each day. We know that omega is equal to change in angular position, which is 1 pi, 2 pi's over delta t. It is equal to delta theta over delta t. Delta theta is 2 rotations, which is 2 pi. Delta t, it is 2 days. I gave it to you. Yes, each one day is 86,400 seconds. So it is equal to 4 pi over, if I need to convert the day to second, I have 1 day over 864 seconds. This is equal to 1. So I need to, the day, 1 day, I have it here. I will do it like this. 864 over 1 day. This is in seconds. So the day will go with the day. 1, it's 1, it's the same one. So omega will be 4 pi over 86420. It is equal to, we can keep it like this, but if we need any number, it's 4 pi over it is 1.454 something multiplied by 10 to minus 4 radian per second. This is omega. Now I didn't ask anything yet. I just found omega. Okay, the first thing, satellite angular velocity. Okay, which is omega. So 1 or A, it's omega, which is this one. This is A. B, satellite's distance from the center of Earth. I didn't give you the radius of rotation from the center of rotation from the Earth. We need to find it. Okay, we have many equations, many relations to use. We have the gravitational force is equal to G, the mass of the satellite multiplied by the mass of the Earth over R squared. We have also in Newton's second law, it is F is equal m multiplied by the acceleration. But this acceleration is the centripetal acceleration or radial acceleration. We know it from before. It is m v squared over r. V is the tangential velocity. Both forces are the same. Okay? Both forces are the same. So, and also we know that V is equal to R multiplied by omega. I wrote it there yesterday, right? So we have three relations. The force is the same. So we can write it like this. This is gravitational, this is centripetal force. They are the same. So the force is equal to G M, capital M over R squared, which is equal to M V squared over R, which is equal to M V, it is R omega. So it will be R squared omega squared over R. We have here the tangential velocity, we don't need it. Let us keep it, this relation, keep it, we'll use it again later. Now this is equal to this. The mass of the satellite is the same. We can cancel R with square here. Okay? Multiplied by R here to there will be G M is equal to R squared multiplied by R. It is R cubed omega squared. The mass of air is given. G is given, it's constant. Omega is given. We can find R. Okay. From this relation, we can reach Kepler's third law, which is, we will see it. Okay, now we have R cubed is equal to G multiplied by the mass of the air over omega squared, which is equal (6.67) multiplied by 10 to negative 11. The mass of the earth, it is 6 multiplied by 10 to 24 over omega squared, this number. Using this alpha G, shift alpha C. ضرب 6 في 24 تكسير. This is R cubed. It is equal to 1.89 something. We can assume it 1.9. Approximate it. 1.9 multiplied by 10 to 22 meter. It is radius. So the unit is what? Meter, right? But now this radius is cube. It is not volume, okay? Meter cube. So meter cube. We need the radius. From this, the radius, we need just to take the cube root to have R. So to another step. So R is equal to the cubed root of that, 1.9 multiplied by 10 to 22 to the power third, which is the cubed root. Then R is equal to 266 492 492 18.8 approximately meter. It is almost 26 point something thousand kilometers. So R, it is almost 26.63 multiplied by 10 to 6 meters. This number. Okay, this is R. Now we can find that. What about C? Tangential speed. We need to find V. Okay. Omega, we know it. R, we know it. What is that? Velocity. The speed, the tangential speed. It is equal to R multiplied by omega. This is R. This is omega, which is 266 492 18.8 multiplied by this omega, which is 1.45 multiplied by 10 to minus 4. So it is equal to 3,864.1, almost 4 meters per second. It is 3 kilometers, 3.8 kilometers per second, which means almost, it is more than 2 miles per second. The rotation of this satellite about that. It's fast. Any question about this? This is T. D, satellite centripetal acceleration. A centripetal is equal to V squared over R, or R squared, if I use this, omega squared over R, because V is R omega. R will go with R with square, so it is R omega squared. Both of them will be the same answer. So that's V squared divide over R. It's 0.560 something meter per square second. Okay. So this is the acceleration. طيب. The gravitational force. We need the force to gravity. Is equal to G M mass of the earth over R squared. We know everything here. G is known, M is known, which is the mass of the satellite, the mass of the earth. R is known also. I'll find it directly. It is equal to 1,693.65 newtons. It's a force. Look. This is a gravitational force. If I ask you, what is the weight of this satellite at Earth's surface? You will tell me simply it is the weight, which is the gravitational force at Earth's surface, which is mg, which is equal m multiplied by g. Assume it not 9.8, assume it 10. It will be 30,000 Newton. Right? This is the weight, almost the weight of this satellite on the Earth's surface. Now, which is the gravitational force? If I ask you, what is the weight of this satellite at that position, it is just 1,693 newtons. That is why, if you see the difference or the ratio from this gravitational force or the weight here away from the Earth and the weight at the surface of the Earth, this ratio, because of that, I will show you something. I need to find the ratio, which is 1,693 over 30,000. It is 0. It is 5.6%. 5%. So the weight of any object at that position is 5% from its weight at the Earth's surface. Because of that, we say out in the outer space there is no gravity. No, there is a gravity, but the effect of this gravity is 5%. Is that clear? The weight at Earth's surface 30,000. The weight or gravity force is 1,693 newtons. This is the ratio, 5%. Because of that, everybody say there is no gravity in the space. No, there is a gravity, but it is 5% or less. If we go further, more, then it will be more or less. Okay. The next question is about the tides. There is nothing to solve in this topic. We need just to talk a little bit, and you saw everything in the video, and you can see that in the notes. How many tides each day? We have 2 high tides and 2 low tides, as you know. Also, we have 2 cases, the sun has an effect on the tides. If the angle between the moon and the earth and the sun is 90 degrees, as you see, the tides will be the lowest. There is a name for these tides. It's neap tides. If the angle between the moon and the earth and the sun is 0 or 190, 180 degrees, then you see spring tide, which is the highest. So, because the gravity now from the moon and from the sun is the biggest. And it is different from day to day, from place to place, and in 3 dimensions. Sometimes you can see that in the right side of the picture. If this is the earth and this is the sun, the rotation of the moon about the earth, it is not in the same level. There is an angle. It is almost 7 degrees. So the moon is rotating like this and has an angle. And it is going from here to here. Because of that, we don't have ellipse, no ellipse or eclipse each month. So sometimes the moon is here, sometimes the moon is here and here and here. The place of moon will change the altitude of that time. But we are care about the main two ones, which are the neap, as we see, and spring. That's all, I think. Any question about them? Now we have Kepler's law or laws. The first law says that the contour or the trajectory of rotation is an ellipse. The ellipse is just a closed shape. Circle is a special case of the ellipse. I don't know if this is circle. The circle has one center. Actually, it has 2 centers, and both of these centers are at the same point. If we just push the ellipse like this, these centers will come to be one center and the shape will be a circle. The planet orbits are ellipses, okay? The moon orbit about the earth is ellipse. The second law, which is the law of equal areas. When the object rotating about another object, Earth about Sun, satellite about Earth, Moon about Earth also. If we have equal period of times, assume this, for example, 1 day. And this is also 1 day. The area, as we see from the video, this area, A1, will be equal to A2. They will be equal. So this line, this radius, will span equal areas in equal times. Okay? Because of that, we can find this bit of information that the moon or earth here is faster Here it is slower. And also, if the orbit is bigger, then the rotation is also slower and slower. For example, for Pluto, I think the period of it is an 18, no, it's more than 200 years. Some planets has 10 years, 15 years, and so on, 80 years. No, I think Pluto is 80 years, 80 or 81 years. Okay, this is the second law. The third law, it is the ratio between the time period and the radius. We can find that from here, and you can do that. We know that the force is equal, we just say, see it, over R squared, which is equal to mv squared over R, which is equal to, again, R squared omega squared. Okay, R will go to the square, so we have R omega squared. But you know that omega is equal to 2 pi multiplied by the frequency. We need to use that in the next part, which is equal to 2 pi over t, which is the period. We have it squared, so this will be equal to m r 4 pi squared, because I need to square everything here, over t squared. Okay, this equal to that. The mass from here will cancel the mass here. Now I need just to order things. So I have Gm. I will multiply it by t squared. I will multiply this r squared with here. It will be equal to r cubed by 4 pi squared. So I have it like this. At the end, r cubed is equal to Gm over 4 pi squared. I divide over this, multiplied by t squared. So I have r cubed is proportional to t squared. This is the third law for Kepler. Kepler came before Newton. These laws came after Newton. But Kepler know that before these laws. Okay? You can see it in the notes. P is the period, A is the radius. Okay, that's all for Kepler's laws. Any question about them? The waves, page number 3. Maybe I have just one problem, and the rest of the review is just the lecture. There's nothing new to say about it. And there's no calculations to put, and just a concept question. Now, we have this way. You will see something like that in the example. We have the amplitude here, A, which is the maximum displacement. It is equal to 0.2, the units in meters, because this is y in meters. And here, the time in seconds, I think. Right. And also, in the graph, it is given that from here to another here, this distance in time, time distance, it is the period, which is 4 seconds. What else? Nothing. That's all. I need you to compute some other quantities knowing the amplitude and the time period. If I need anything else, need another information, I will give you that information. So A, what is the frequency? It is 1 over T. So it is 1 over 4. You can, maybe when you see that this shape in the exam, maybe you need to take your information from it, from the shape. 1 over 4, it is 1 over 4 or 0.25, the units is hertz. Means we have a quarter wave each second. B. The angular frequency, omega. It is the angular frequency or the angular speed or velocity. It is equal to 2 pi f or 2 pi over t. So it will be equal to 2 pi over 4 or 2 pi multiplied by quarter. I will find it as a number 2 pi over 4. It is 1.57. That's enough. 0 something. What is that unit? It is radian per second. Okay, what else? C. If lambda, the wavelength lambda, is equal to 2.5 meters, the wavelength is 2 meters. Find the speed of the propagation of that wave. V, we have a relation. V is equal to lambda multiplied by the frequency. So it will be equal to lambda is 2.5. The frequency is quarter. .625 meter per second. It's a velocity. It is 60 centimeters per second. Just like a wave of water, slow wave. Okay, what else? See, now we have D, the amplitude. The amplitude A is given from the graph, which is how much? 0.2 meters or 20 centimeters. What else? E, the position, velocity, acceleration relations. I'll change this. The relations, they contain sine, cosine, or something like that. If you remember, x of t as a function of t is equal to the amplitude cosine omega t plus phi, and always I told you phi is equal to 0. It is not 0 here, but I will assume it's 0. It's okay. Okay. Now, what is x? X of t is equal to the amplitude. We know the amplitude. It is 0.2. Cosine. What is omega? We found omega. It is 2 pi over 4. You can write it like this, or you can put this magnitude. Okay, it is 1.57 multiplied by t. That's it. This is the x relation. What about the velocity relation? The velocity as a function of time, it is equal to negative omega multiplied by a, but we have sine omega t. Okay, we have everything. So it is equal to negative omega, it is negative 1.57. A is 0.2, sine 1.57 t. That's it. What about the acceleration? The relation of the acceleration, it will be given with you in the formula sheet. X of t, v of t, a of t, they will be given as this one. It's negative omega squared a, again, cosine omega t. So it will be equal to negative omega 1.57 squared, it's a number, multiplied by 0.2 cosine 1.57 t. That's it. You just compare the given equation with your information. Omega a, t is t, the time. Any question about these? Online? Okay, what else? EF, if the mass is how much? 4 kilograms. Find the force and the momentum. The force is equal to the mass multiplied by the acceleration. Simple. Which is equal to the mass multiplied by that acceleration, which is 4 here. And we have negative sign from the acceleration. It is 4 multiplied by 1.57 squared multiplied by the amplitude, which is 0.2 cosine 1.57 t. This is the acceleration. This is the mass. It's Newton's second law. We know it. And as I told you, the final exam is not comprehensive, but our material depends on the first material. Okay? What about the momentum? The momentum P is equal to the mass multiplied by the velocity. This is the velocity. And the mass is 4. We have a negative sign from the velocity. And we have 1.57 multiplied by 0.2, which is the amplitude, multiplied by sine 1.57 multiplied by t. This is the moment. Any difficulties in this? Again, the exam will be more simple than this. Okay, the final thing. H. I gave you 2 choices. The first one, if we are dealing with spring mass system. In this system, we have omega is equal to the square root of K over M. Yes, K over M. If you are dealing with pendulum system, omega is equal to L over G or G over L. I think G over L. Yes, it's G over L. The mass is given, it's 4. I need to find K. From here, I will put it here. Omega square is equal to K over M. From this, K is equal to the mass multiplied by omega squared, which is equal to 4. The mass is 4. Omega 1.57 squared. This is K for the spring. If we have a spring, you can see that in page 3 we have a mass spring system. From here, if we have a pendulum system, we have omega squared is equal to G over L. From this, L is equal to G over omega squared. G is known. It is 9.8 over omega squared, which is 1.57 squared. So this is the length of the string. So we have two relations, which are omega squared K over M, omega squared G over L. Any question about this? Now that's all for the waves. Let us move to the next page. This is the same as the lecture, but let me share the monitor. Can you see my monitor? Okay. Okay, now just to say that again, we have two kinds of waves, which are longitudinal or longitudinal and transverse. You need to know the difference between them. We have in both of them, we have a wavelength and we have amplitude. Lambda is equal to the velocity over frequency we just applied. An example on that, we have this example, we talked about it in the previous lectures. This is all about sound. The main thing we have different sound speed in different materials. We have a limit for human to hear from 20 to 20,000 hertz. We have frequencies above 20,000 are ultrasonic. Frequencies are below 20 hertz are infrasonic. Each creature has its region to hear from. Okay, and we have this example. We solved it, which is the speed of sound. It is just the velocity the velocity of the sound is the distance over the time period. We know that. We have a new thing I will talk about, which is the echo Doppler effect. Doppler effect, yes, we have, for example, observer A, observer B, and observer C. If the car is moving to the right, to the direction of observer A, he will hear the sound louder and the frequency higher. The observer B will hear the frequency lower. And observer C, his his place or his vector position is perpendicular to the motion. So there's no changes. There's no changes will happen to the sound for the observer see. He will be, that is when the car or the truck perpendicular to his place. Also the driver, there is no changes of the sound. That's all for today, but I didn't put any review on what? On the pressure and the density, because when I look to the examples on the lecture, they are the same as the examples I need to use in the review. So it's the same as the lecture. It is simple. It is a simple formula. You need to solve it just like that. And the echo, if you are away from a mountain, for example, as always, if we have a mountain, and this is me. If I need, and the distance between me and the mountain is X. If I send my voice, I need to hear it after it come back, which is 2x, not just one x, x and another x. Okay? This is an application on sound. The velocity of sound is 300, almost 40 or 43 meters per second. I think that's all. As I told, I will try to collect the formulas. Also, the initial material formulas are important to be with you, to use them. As you see here, we just use Newton's law and velocity, the acceleration, the momentum, the force. And I will stop recording here because stop recording.